Hi everyone. So I'm going to present to you a free central limit theorem for dynamical system. So free probability is a field of growing interest, notably because of its deep connection with random matrix theory. And one of its fundamental theorems is a free central limit theorem. In the paper I'm presenting to you, I relax one of its key major assumptions, free independence, by introducing for the first time a notion of free mixing. By doing so, I obtain second and third order limit results for ergodic theorems, and I hope to convince you that it's of great interest for random matrix theory. Please note that I also generalize it to use statistics, but I will not have time to dive into this. So to make things short, free probability is a field of probability that studies non-commutative random objects, and it does so by abstracting random variables as operators. To fix matters, I'm going to take A to be a von-Neumann algebra, tar its adjoint operator, and tau its trace. If you don't know what that means, you can think of A as the algebra of random matrices of size n with bounded entries, and tau the expectation of a trace we normalize. One of the key concepts of free probability is the notion of free independence. And in its most classical statement, we say that x and y are free or freely independent if all polynomials of x and all polynomials of y but of trace 0, this alternating product here is also of trace 0. And so notably, this alternating product here. And so notably, we can hope for x and y to be free only if they are very far from being non-commutative. So keep on mentioning free central limit theorem. What is it? It states that for a sequence of free independent copies of an operator x that is centered and we normalize, then the empirical average is asymptotically semicircular. This is a beautiful theorem, and it's striking in its resemblance to the classical central limit theorem, where here instead of getting a Gaussian limit, I'm getting a semicircular limit. Why is this interesting for random matrices? Well, let's take X to be a Gaussian matrix, then it actually has the same distribution as an empirical average of independent copies of itself, Xi's, we normalize by square root of n. This is true because the underlying distribution is Gaussian. And we know that two independent random matrices in the J, U, E ensemble are almost free. And so here, hopefully, we are looking at an empirical average of operators that are almost free. And so the free central limit theorem should allow us to study the empirical eigenvalue distribution of X. But what if X has dependent entries? Then sadly, we cannot follow the same line of reasoning because we know that independent matrices that have dependent entries are not in general asymptotically free. But I propose that we look at it at a different angle. Instead of, we can rewrite X as a dependent sum of matrices that all have independent entries. And hopefully, if the dependence of the entries of X, the original matrix X, are small, then we can rewrite it as a sum of slightly dependent random matrices. And hopefully, matrices that are slightly dependent are also slightly unfree. And so if we could relax the free central limit theorem to tolerate a sort of free mixing sequence, then we could try to use our generalized free central limit theorem to study the eigenvalue distribution of X with X having dependent entries. And so this is what we propose to do here, following decades of development in classical probability that have massively relaxed the condition of independence for the classical central limit theorem. We ask the question, can we do the same thing for free probability and for free central limit theorem? The answer is yes, and this is what I'm presenting. To situate that in the literature, there has been a lot of work looking at matrices with dependent entries or exchangeable entries. This is not new. However, there has been little work relaxing the condition of free independence in the free central limit theorem. The most interesting relaxation is probably the one that is relaxing it to freeness with amalgamation, which is a notion that is, if you want, conditional freeness. But conditional freeness is very far from mixing, or allowing mixing sequences. We cannot study stationary sequences with that. And this is the gap we hope to fill. To fix matters, I'm going to take Xi to be a stationary sequence in meaning that its distribution is left by undershifts. To fix matters, I'm going to say for O subset n, I'm going to denote Fn be a unit or algebra that are generated by xi for I belonging to the subset n. In classical probability, this is the sigma field of events generated by xi for I belonging to the subset n. I'm going to denote F infinity, the tail algebra. In classical probability, this is the tail sigma field. Going to denote E, the non-commutative conditional expectation on the tail algebra. Note that the tail algebra is trivial if my process is freely independent. However, it's not in general trivial if I'm looking at freeness with amalgamation. I'm going to note by F0 of n all the elements of Fn that are centered and that are bounded by 1. If you want, those are my indicator functions. And so in the classical probability, I measure the dependence by looking at all the events that depend on x0 and the past of x0 and all the events that depend on xi and the future of xi, and then bind the dependence between those. This is what I do, but it's a bit more technical because of the non-commutativity. So here I look at all operators, y1 and y2, that are in f0 of L until infinity, so all the algebra generated by xi, the future of xi, and all operators z1 and z2 in f of f0 minus infinity to 0. And I bound the L1 norm, if you want, of the non-commutative expectation of z1, y1, z2, y2. So this, once again, alternating product. If my process was freeness with amalgamation, free with amalgamation, then my free mixing coefficient would be equal to 0. So I'm indeed measuring something that makes sense. However, note that my mixing coefficient can be equal to 0 and my process can be not free with amalgamation. This is because I'm looking here only at an alternative sequence, z1, y1, z2, y2 of size 2 and not infinity, as in the classical definition of free mixing, free independence. So what did I do? I defined the notion of free mixing. Is it useful? Yes. I'm going to present the following theorem. So if I have xi, a stationary sequence of self-adjoint free random variables that are centered, and if my free mixing coefficient decreases enough, fast enough that this sum is finite, then my empirical average is asymptotically semicircular. And I can also get a very same type of bound by bounding the the distance between the still just transform of my empirical average and my limiting object. And this is going to go down to a speed of 1 over square root of n. Please note, however, that here my radius can be operator valued if for example, if my sigma field is not trivial, if, for example, I have freeness with amalgamation. I also generalize this to general dynamical systems that are generated by an action of an amenable group on an operator X. There's going to be subtleties and complications due to topologies of a group, etc., etc. And notably, is going to slightly change the requirement on how fast my mixing coefficient have to decrease. Those will depend on the topology of a group. I also relax it to triangle arrays and L2 plus epsilon a non-commutative L3 space. And like in classical probability, how fast my mixing coefficient decrease will depend on how big 2 plus epsilon is. And also generalize this to use statistics, as I mentioned. Note that I can also make the dimension of my use statistics grow with n. So to go back to my motivating spiel or example, imagine I have here a stationary sequence of self-adjoint random matrices. Suppose that I'm going to denote by alpha the strong mixing, classical probability strong mixing coefficient. Imagine that the distribution is jointly invariant under conjugation by a unitary matrix. Then I can bound the 3 mixing coefficient by the alpha mixing coefficient. I obtain this inequality. It's the free mixing coefficient is smaller than a constant times my original alpha mixing coefficient plus 1 over n. And so the free mixing coefficient that I introduced actually makes sense. And the answer is yes. Random matrices that are almost independent are also almost free. application example, imagine I have a random matrix with independent diagonals. So diagonal here is all the xij for ij of a distance of r or minus r. So imagine I have a diagonal with independent diagonals, but inside the diagonal, I'm going to have a stationary Gaussian process that with a dependence measured by a alpha mixing coefficient, alpha r. Then I can actually rewrite this random matrix here as an empirical average of a stationary sequence of Gaussian random variables, Gaussian random matrices. And I can bound the free mixing coefficient of those matrices by the alpha mixing coefficient of those diagonals. I so obtain this inequality here. To give intuition here, we look at the case where n is equal to 2. And so we have here two diagonals, x11, x122, and the other one is just made of one element, x12. So x12 is independent from the diagonal x11, x22, but there can be some dependence between x11 and xs22. And I can actually indeed rewrite this as this sum, which is a sum of dependent matrices, but with independent entries. And this is a key motivating examples for the work I did. So I hope to explain to you why this was interesting, to convince you, sorry, that my development are interesting for random matrix theory. And if you want to check out more, there is the link of, in the first page, there is the link to my archive paper. Thank you very much for listening. And if you have questions, you can contact me during the live session.